Alright, so now we're going to start. So, I guess we can start with questions because we have a quiz. And I know I promised Ashley that we wouldn't have a quiz today, and she asked me, can you please have it tomorrow? But I already printed them, and I can't bother. Like, I have to bring them back now. And you can make it a takeout quiz. So, you know, I'm thinking a little bit.
So you're gonna go buy some Uber Racing
I'm kidding. It's no good. I couldn't resist.
Wait, you signed your quiz already? We asked questions for us. You can't throw us off. How would you not be nervous if some questions have not answered?
Not right now. So, we're just going to finish up the examples we started last time, and we're going to just move on to 3.4. And I guess homework questions on 3.3, we'll just take care of them tomorrow, because for 3.4 you have to do everything in 3.3 anyway. So most of 3.4 is just a revision of 3.3, so I figured if we go through it again today and tomorrow you still don't understand, then we can go over them all at once. But yeah, to do 3.4, we're going to need to do everything in 3.3, so today you should be getting some extra practice on that. So it's curve sketching, which we actually did last class, but even though technically we weren't supposed to do, we were supposed to stop right before the sketch. But we actually went through it. But now we're going to officially do curve sketching. So in your handout, I have the steps and just a few comments back in front. So I think we will go through this together and then, yeah, take it from there. Handout. Okay, so as I mentioned here, having done 3.3 and 1.6 will actually be a pretty important section in today's lecture as well. We've done most of the legwork we need for curve sketching, so now we're just going to put it all together. So here I have the steps for sketching some random curve, right? So on the final, especially, you're guaranteed to have a question where they're going to say, sketch the graph of this function. Right? And what are the things you have to do in order to do that? Well, it's all the steps here. So the first one is, again, most of this is 3.3. Figure out what your domain is. That will come in handy, knowing where your x values are defined, where your function is defined. The second step is to find the x and y intercepts. That's always important, and I actually reminded you here how to do that, right? To find the x-intercept, you said y equals 0, solve for x. Find the y-intercept, you said x equals 0, solve for y. And the third thing you're going to want to do is find asymptotes. Now last time we didn't talk about asymptotes, but now it's going to be an issue for us. So this you actually did in 1.6. If you don't remember that, I put a little stuff here to remind you about what that involves. So there are two kinds of asymptotes we care about. There are more, as you can see from the footnotes, but we're not going to worry about them. The ones we care about are vertical asymptotes and the horizontal asymptotes. Horizontal is the one that we're dealing with here. To find a horizontal asymptote, you're going to take limits, basically. Find the limit as x approaches infinity of your function. Also find the limit as x approaches minus infinity of your function. And if either of these give you a finite number, you just get a number, 0, 1, 4, -5, doesn't matter. Once you get a finite number, then y equals that number is going to be your horizontal asymptote. Right? And we're going to see examples of where that applies. And you should know that it's possible to have more than one horizontal asymptote. So it's not good enough to just take the limit as x goes to infinity. You also have to do as it goes to minus infinity. It could have two different ones as it goes into the different directions. So you have to check both limits. That's important. Vertical asymptotes, you are going to figure out where does, if there's a finite number that your function shoots off to infinity or goes down to negative infinity, right? So for, this is just a little number. So for vertical asymptotes, this is just going to be a number a such that as your limit as x approaches a, your f will just either shoot up or it will shoot down or something like that will happen, right? So to figure out when that happens, you have to figure out where will your function, where will the limit approach infinity of your function. And I mentioned here specifically for rational functions, because those we'll encounter all the time, it occurs, this sort of behavior will occur when your denominator is 0 and your numerator is non-zero at the same time. Okay. And I mentioned here, if both numerator and denominator are 0, it means that you could factor the numerator and factor the denominator and cancel that point, right? So it won't be an asymptote anymore. It would sort of be a whole, right? I don't know if we have an example like that. I think I did do one before. So just give a trivial example of what I'm talking about. Let's say I wanted to graph f of x equals x squared minus 4 over x plus 2, right? Now, obviously, at x equals minus 2, there's a problem, right? However, I know that I could have factored this into x plus 2, x minus 2, and technically I would be able to cancel this, and really my graph will only look like x minus 2. The problem is, the original function had this in the denominator, and so I still have to avoid x equals minus 2, and that's why at minus 2, I would have a hole at minus 4, right? So I put a hole there. It won't be an asymptote because technically the numerator is killing the part that's making the graph blow up. But at the same time, I actually can plug in x equals minus 2, so the result will be what we call a hole, right? So, but as long as you can't do this, you can't cancel and get rid of it, you'll have instead something like this happen, an asymptote. Right. Again, you can have several vertical asymptotes, so you always have to try to find all these possible numbers where it could happen. And another thing that I see students get confused about all the time, so I thought I'd mention it, is it's possible to cross horizontal asymptotes. It's not possible to cross vertical ones, right? So if your function has a horizontal asymptote, it's okay for your function to go across it and then eventually settle to it. That's completely fine. If you have a vertical asymptote though, you can't cross that line, right? Because usually what that means is division by 0, right? That line means division by 0. You cannot cross that line. But your y value, you would in some cases be able to cross your horizontal asymptote. So keep that in mind, right? So don't be like, I know the graph should look like this, but I can't cross that horizontal asymptote. So you make up a graph on your own. I see people do that all the time, right? Because they're afraid to cross this. You can cross horizontal asymptotes in general. It's the vertical ones that are the bad ones. So I thought I'd mention that. Then obviously you need to find your intervals of increase and decrease. When is your function going up? When is it going down? Right? And maximums and minimums. And you use the first derivative for that and the first derivative test. Right? So I told you that here. Next thing you're going to want to do is find the intervals of concavity and where your inflection points are, and use the second derivative test and the concavity test for that. I put a footnote there. Okay, yes. Remember, when you're finding the location of points, you use the original function, right? So if I know this is a critical point, I know it's a maximum, I want to find the coordinate, I have to take that x value, plug it into the original function, not the first derivative, right? Or the second derivative. When you find the location of points, use the original function. And step 6, finally draw the graph, right? So you're just going to put all this information that you had on a pair of axes and make sure your graph will fit all these features. The book also talks about symmetry. Sometimes symmetry might help you out a lot, but following these steps, you don't really have to worry about symmetry. It will sort of show up anyway. I don't think you'd have to concern yourself with a whole extra step for symmetry. Following these 6 steps will be good enough to graph any function that we're going to ask you about. And anything more difficult, use a computer. Okay, rookie mistakes. Mistakes that students always make that I've noticed over the years of teaching and tutoring. Obviously, they're the mechanical ones. They mess up the algorithm, mess up the derivatives. Okay. Forgetting steps is another mistake, right? You're in the test. Okay, I found intervals of increasing, decreasing. Now what? And then you just get stuck, right? Don't forget the steps. Practice problems over and over. That will help you not to forget the steps, right? Because if you go and you ask me, okay, what do I do next? I can't answer that question. Okay, that would be cheating. People have asked me questions like that before. Okay, so I found the intercepts. Now what? You're in a test. You're supposed to know what's next by now. Okay. The biggest mistake I've seen so far, which I think is crazy, is students ignoring anomalies. Anomalies is something that just doesn't fit. So they might go through and they might, they find their x-intercepts, right? And then they're like, okay, there are 2 x-intercepts. And then they draw a graph and it has 3 x-intercepts. Obviously over here you told me there are 2. Right here you drew something that has 3. A mistake was made somewhere, right? You're just like, oh yeah, that's the graph. No, it's... Obviously something is wrong, right? That's like you trying to sell me a car and tell me it's good to go and all the wheels are missing and there's no engine, right? Like, you can't try to sell me that car and I'm like, obviously it doesn't have what it's supposed to have. It's something that's supposed to be glaring. It's one of those things, you're just counting stuff, right? You saw something that has 2 x-intercepts, don't draw a picture that has 1 x-intercept or 3. If something else tells you that, it means somewhere a mistake was made. You need to find it and fix it, right? Don't just be like, nothing's wrong in this type of thing. But I see that all the time. People not giving me enough intercepts, or they'll have, in their picture, and on their first derivative test, it shows that they have 2 maximums, but on their graph, there's only 1, or there's 3. Like, mistakes like that shouldn't be made. I'm just saying. But I've seen that before. Make sure none of you make that mistake. Other rookie mistakes is forgetting what function to use, right? So remember that table I gave you about f and f prime and f double prime, when you should use them, what each tells you, that sort of thing, right? So if you're looking for a coordinate and you want to find a y value and you plug that value into this first derivative, obviously you have no idea what's going on. First derivative does not tell you about coordinates on the graph. It tells you about increasing, decreasing, and the x values for maximums and minimums, right? You should know that that's not what you would use to locate a point on the graph, right? So you need to know how to use which function and what to use them for. Otherwise, there is no mercy, as I put here. Because that's just, it's just one of those things that, again, just shouldn't happen. It's like, I want to heat up some food, and you put it in the freezer, right? That means you have no idea what the freezer is supposed to do, and that it's sort of not doing what you intended. No, you don't put food in the freezer to heat it up. You put it in the stove, or on the stove, or in the oven, or in a microwave, right? It's exactly the same thing I see when I see people trying to find coordinates and they're using the first derivative. It's sort of like, what are you doing? Right? I obviously cannot believe anything else you say at that point. Like, I'm just going to walk away. Right? So I'm just going to walk away. So people ask, so, I want to find this point on the graph. I put in the first derivative, right? I'm just going to walk away. I'm not even going to respond. It's not something that should happen. Know what each function does, right? Know what the original graph gives you, what the first derivative gives you, what the second derivative gives you. I gave you all that information in the table last week. Make sure you study that table and know it, right? Know when to use which function. Okay, and after that spiel, so these are the steps we went through last time. So I'm just here, and we have them in writing to help you study. And we did a bunch of these examples. I think we did 4 of them for 3.3. I think it's instructive for me to finish off the last 2, and then we're going to do the examples for 3.4. I have 3 of them. So the examples for 3.4, I sort of made them look more like what it might show up like on a final or a test. So the thing is, on the final or a test, they're going to give you the function, and they're also going to give you the first and second derivatives. You won't have to find this, usually, right? More than likely, you'll get the derivatives, right? Because a question like this is not testing your ability to take derivatives. It's testing whether you know what derivatives can be used for. Right? That's the whole point of this example, this kind of problem on a test. So you'll be given the function and they'll tell you the derivatives. You don't have to verify them. You just assume they're right and you do the problem with these derivatives. So, right? So for those examples, I gave you the function, the first derivative and the second derivative, and we're just going to use it. But for now, for 3.3, that's where we're doing everything. So I guess we'll just pick up there with the fifth example. So the problem is to graph this guy. Find all the things you need to graph this guy. But x equals 2x to the 5 over 3 minus 5x to the 4 over 3. Okay. All right, what's the first thing we do? Domain. What's the domain of this guy? Everything. These are the cube roots, right? Notice that the power is in the thirds. That means there's a cube root being taken. Cube roots don't care about negatives or positive. In general, anyone can work in a cube root. So domain is everything. How about intercepts? Let's worry about the x-intercepts. Where does that happen? So you set that equal to 0, set y equal to 0, you're going to solve for x. How do I solve that? Factor, right? So x to the, what do I pull out? 4/3. Pull out the lowest power. This leaves us with 2x to the y. 1/3, right? You take 5/3 minus 4/3. Minus 5. And you set that equal to 0. This, of course, means x equals 0, or x equals, you bring the 5 over, divide by 2, and then you take the cube. So that's 125 over 4. So those are your x-intercepts. Your y-intercepts, just y equals 0, you just, that's actually 8. So you plug in your x value is equal to 0, you obviously just get y equals 0. So those are your intercepts. What's the next thing? Increasing, decreasing, max and min. Right, all that is taken care of in one step because all that comes from the same guy, first derivative. Of this function, what is that?
10.3x. Minus.
So I'm going to want to factor this, so what can I pull out? 10 over 3 x to the 1 over 3. And what would I have left over?
X plus 1 over 3. X 1 over 3, all 1.
So the 1 over 3 minus.
Minus 2.
Okay, so now I need to find the critical points, right? Critical points. Where do these happen? Wait, what's undefined? What? It's not undefined. So you set these guys equal to 0. So this means x equals 0. Set f prime equals 0 or undefined. And this is defined everywhere. So we just care about this guy. So that means x equals 0 or x equals what number? 8. So now you're going to test this in the first derivative test. 0, 8. So you plug in random numbers, right? So you go over here, like -1, positive 1 will work here, 9 will work there. And you're going to plug these guys in. Now if you take a negative number to the cube root, you get a negative number, right? Cube root of negative 1 is again negative 1, so it's negative times a negative. So this is positive. What does that mean here? Increasing. Plug in 1, this is positive, that would be negative, right? So it's positive times negative. That means decreasing. And you plug in 9, right, 9 to the 1/3, this will be positive, and this factor is also positive, so this is again increasing. Do we have maximums or minimums?
Yes. Relative max at 0 and close to minimum.
Right, so there's a maximum here, there's a minimum here. Alright, now what? Huh?
Find the max and min.
Yes,
So we'd like to write down our findings so we have it in a nice place. Okay, increasing, where is it increasing?
Negative infinity to 0. And union 9 to infinity. 8 to infinity.
8 to infinity. Decreasing between 0 and 8. The maximum occurs at 0, 0, right? Because you just plug in into the y value. The minimum occurs at 8, what? You'd have to plug that in, right? So here you have 2 times 8 to the 5/3 minus 5 times 8 to the 4/3. Cube root of 8 is 2 raised to the 5th. You got 32 times 2, 64. 2 to the 4th is 16 times 5. 16 times 5? And what's that?
Negative 16.
Okay, so negative 16. All right, now the next thing we do. Well, we have to find the concavity and inflections. What tells us about that guy? The second derivative, right? Which is, in this case, going to be what?
This is going to be 20.
1/9 x to the? Minus what? Okay, we're going to factor that. What do I pull out? Minus 2/3. Pull out the lowest power. What would be here? Just x to the 1, right? Because if you add 1 to minus 2/3,
It's going to be negative 1/3.
negative what?
1/3. It's going to be negative 1/3. That's what I'm saying.
Right, when you add minus 2/3 to 1/3, you get minus 1/3, so that works out. And this is just going to be 1. So,
X equals 0 and x equals 1.
critical points. You set f double prime equals 0 or undefined. So for x equals 0, this means x equals 1. For undefined, x equals 0, right?
Yep.
Because this is actually, negative power means 1 over x. You divide by 0 here, so it's undefined. Now you do the test in the second derivative. Testing random points, negative 1, maybe a half here, 2 here. So we plug in negative 1 into this. This gives you a negative, that also gives you a negative, negative times negative. Positive, what does positive mean? Concave up, like a cup. Plug in a half. The cube root of a half is going to be less than 1, so that's negative, but this will be positive, so this would be negative here. Means concave down. Plug in 2. All right, the cube root of 2 would be bigger than 1, so this is positive. This will also be positive. So concave up. Do we have inflection points?
Yes.
And 0.
At 1, we have an inflection point. We do not have an inflection point at 0. Why not? It's undefined there. Inflection occurs when it's 0, right? And it changes sign, right? So that's going by the definition. So no, this is not inflection.
Wait, it can't be 0?
F double prime is undefined. Right? So inflection occurs when it's 0 and it changes sign. But so that 0 is obviously going to be a weird kind of point. So let's actually see what kind of point it is. So now we're going to list our findings. Where is it concave up? Where is it concave down? Where do we have an inflection? We're concave up on negative infinity to 0. We're concave down between 0 and 1. Inflection point would occur at 1 comma, plug in 1 into the original function, minus 3. Okay, that's all we need. So now we can actually sketch the curve. Can I fit it here? So it's long. These are long problems. I'm not going to lie. But if you get into the groove of things, it shouldn't be bad. And like I said, on a final, more than likely, they'll actually tell you these derivatives. You won't have to find it. You just have to know to set them equal to 0, what to do with it. So now let's start to put all this stuff on the graph. So let's do with our intercepts. 0 is an x-intercept, and 125 over 8. Let's put that here, 125 over 8. Okay, so those are the intercepts. I know where I'm increasing, right? So up to 0, from 0 and everywhere. Let's write this over.
Professor, what if you can't find the x-intercept from the original function? Because sometimes it's like, you can't find it.
It means it doesn't touch the x-axis.
Oh, that's what it means?
Yeah.
It's like, on what sign it was like 2x to the 4th power minus 4. How would you find that?
X to the 4th
Nah, I
power.
made that up, but I'm saying like 2x to the 4th power minus 5. How would you factor that? Like, 2x to the 4th.
Well, that would actually.
Oh, plus 5 and then it's to the 4th power. But the case.
Well, yeah, something like, x squared plus 1, that actually doesn't touch the x-axis, right?
Okay.
So, because that graph looks like this.
Okay.
So if you actually can't solve for the x, it means it doesn't touch the
Oh,
x-axis.
okay.
So in the first one, if you solve for an intercept and you can't solve for it, and then you give me a picture that does that.
Alright.
Right? So yeah, if you can't find intercepts, they don't exist. Make sure your picture doesn't cross that horizontal. Yeah, so now I know from 0 and all the way back, I am increasing, because I'm increasing from 0 to that. From 8, does 8 come before or after this number? So let's put 8 here, and all the way beyond from 8 onwards, I'm increasing. In between, I am decreasing. And I know where I have a maximum that occurs at 0, so this is going to be one of my maximums, so I can write that in. 8 is going to be one of my minimums, 8 comma minus 16. It's going to be a local minimum. Right, this happens at minus 16. That's a minimum. And that's everything we know from the first derivative. Now we move on to what we know from the second derivative. From 0 back, we are concave up, shaped like a cup. Between 0 and 1,
That's a very short portion.
we're concave down. And from 1 to infinity, we are again concave up. we have an inflection that occurs somewhere here. Okay. All right, so that's all our information, right? So everything we've done before is now on this graph. How do we put it together?
Start from 0.
I know I'm increasing here towards 0, right? So I know I'm coming from the bottom going up to 0, not as opposed to this. That would mean decreasing. So I know I have to come here. I'm increasing. How am I increasing? Concave up, which means I should be increasing like a smiley face, right? So my function is going to come up like that. That's how I'm going to approach 0.
So would it be incorrect if you come like this?
Hmm?
If you come like a U shape? Would it be incorrect?
Where?
Yeah. If you start like that.
This is fine. What do you mean a U shape?
Like a U.
You mean if you drew this?
Yeah.
That would be wrong. Why would that be wrong? Because then this point would have been a minimum.
Oh,
You'd have a minimum over here. It's not in your calculations. So you know you can draw a U shape, right? You would have to be just coming up like that. Right?
Showing no minimum.
So those are the things you have to look out for. Could I draw a U shape? You have to think about what would that mean. It means there would be a minimum, right? It's not, there should be a minimum. So it has to come up like that. Now, what are we doing? We should be decreasing this whole time. Now, when I'm between 0 and 1, I should be decreasing, but now I should look like a frowny face. So you see, that's why that point wasn't an inflection. Now it sort of looks like a jagged edge, sort of, almost. So now I decrease concave down. I have to still keep decreasing to this point, but now I'm in the region of concave up. I actually switch concavity here. And now I have to start increasing concave up.
Why you change concave at 1, right?
At 1, yes.
125.
So that's what that function looks like. Smiley face, frowny face, switch to smiley face, and then maintain going all up. Questions on that? Let's move on to an interesting one.
Because at express
Yes.
rate, you change concavity at express rate.
Huh?
Did you change concavity at express rate?
No. No.
yeah, what kind of?
X equals 8 was not an inflection point, so I can't change comparison. I was concave up before it, and I'm still concave up after. Right? On both sides, I should like a smiley face. I didn't switch concavity. Here I switched concavity. I was a frowny face on this side. I'm a smiley face on this side. So there I switched. This one I switched concavity as well, but it's not really an inflection because it doesn't look like that wavy shape. Here I'm smiling, but here I'm frowning. It sort of looks almost like a jagged edge. So
Wait, Professor, I have one question.
yes.
You're saying the origin? Like, how would you know if you are not supposed to change from concave up to down as a smooth?
What kind of inflection?
What do you mean?
Oh, it has to be on the inflection point to be like a smooth change, right?
Yes. You mean if you're coming like this and you want to switch nicely to that,
Yeah.
it would mean an inflection would have to happen here. So we know that didn't happen. So it has to be a very abrupt one because to get the other one, we have to have an inflection. I could even keep all this stuff. Like really, it's just a template. You do all these problems the same way. But this one is going to have an extra part. What's going to be the extra part for this guy?
Yeah, asymptotes.
The asymptotes now are going to apply. So maybe I should erase this because I'm going to stick that extra guy in.
So this section, one problem takes the whole page.
Yes. Okay, this guy is going to have asymptotes. So let's start out our steps. What's the domain here?
1. Oh, that's not domain.
Right, you can't touch plus or minus 1, right? Because that makes the denominator 0. Any intercepts? Do we have any x-intercepts?
Professor, you copy the problem.
On the paper, on the paper.
Oh, okay. So this would be 2, 2. So are there any x-intercepts? Set y equals 0. Are there any intercepts? No real solution. Right? X squared plus 1 is never 0. Right? There's nothing you can, no real number you can plug in there that's 0. What about y-intercepts?
No, the one number negative 1.
This means y would be plugging x equals 0, right? So 0 squared plus 1 over 0 squared minus 4 minus 1 over 4. So this is a function that has no x-intercept, but, so make sure you note that, no x-intercept, but it has a y-intercept. So let's see.
Is it always the case in fractions?
You always, you check it. So, now what's the next step?
Now the next step would be
Find vertical and horizontal.
Let's worry about the asymptotes, right? This is the extra step that we're going to need here.
Wait, so this may be a stupid question, but like in the part where you're solving for the x-intercept,
Yeah.
can't you do x squared versus 4 times 0 cross multiply?
Okay, you'd still get 0 equals x squared plus 1 as well.
Then you get x equals
Right, x would have to be the square root of minus 1, which is a complex number. You can't graph those. Okay, so let's start with horizontal asymptote. Or you can just write H. How do I find horizontal asymptote? You have to approach infinity. You have to take limit as x approaches infinity of your function. And you have to take limit as x approaches minus infinity of your function. And what's the answer altogether now? 1. Right? Ratio of polynomials, highest power is the same, goes to the ratio of the coefficients. Right? So now let's talk about vertical asymptotes. And like I said, for rational functions, it has a trick. Wherever the denominator is 0 and the numerator is not 0 at the same time, it gives you a vertical asymptote. Right? Here, the numerator is never 0, so we don't even have to worry about it. So just set the denominator equals 0. X equals plus or minus 2 are vertical asymptotes.
Oh, you said the denominator equals
Yes. No, numerator equals 0 gives you x-intercept. Okay, so that was the extra bit. Now let's look about increasing, decreasing, max, and min.
When do you know to look for the asymptotes? When do you know you have to look for the asymptotes?
You always look for them. In all my examples before, they didn't exist because they were like polynomials. Polynomials don't have asymptotes.
So when they have denominators, yeah.
Yeah. So here we're going to do the first derivative. What's that? Yes.
is the low behind.
Yes. So it's the bottom times the derivative of the top minus the top and the derivative of the bottom over the bottom squared. Can I simplify that? yeah, only a 2x can come out really. I have x squared minus 4 minus x, so this equals that. I have minus 4 minus 1. So it's just minus 10x over this. Right?
Yeah.
And critical points, x equals 0, x equals 2, x equals minus 2. Set 0 and undefined. Plug that in the first derivative. Test points, minus 3, minus 1, positive 1, positive 3. Okay. Now, notice here the denominator is a square, it's always positive, so numerator is what controls the sign, so that's the only thing I'm going to be looking at. Right? So, plug in a minus 3, so positive, means increasing. Minus 1, positive, still increasing. Plug in a 1, it's negative, decreasing. Plug in a 3, negative, still decreasing. Do we have a maximum or a minimum?
Oh, wait.
There's one maximum that occurs at 0. These are nothing, right? Because it's increasing on both sides. It's not a max or a minimum. Okay. So we're increasing, decreasing, max, min. So we're increasing on minus infinity to 0. That's it, right? We're decreasing from 0 to infinity. Obviously, we're not. I mean, technically, you have to avoid the 2 to touch.
Yeah.
Let us be specific. Right? You have to avoid the negative 2 because your function isn't even defined. And now from 0 to 2, union 2 to infinity, we're decreasing. We have a max at 0, comma, minus a quarter. We have a min, none. So what's the next thing we look at now? Here you look at the second derivative. So it's the bottom times derivative of the top minus the top times derivative of the bottom. Over the bottom squared. Can we make that nicer?
You can take out a negative.
You can take out an x, right? You can take out 10.
Professor, isn't it minus? Wait.
Minus where?
When you do quotient, isn't it the first thing f prime whatever minus the, or did I?
Yes, but there's a negative here.
Oh crap.
So it's minus a minus 10 using that plus 10. Okay, so 10 is a common term, x is a common term, x squared minus 4 is a common term. What do we have left with? Well, we have a minus x squared minus 4 plus, we took out the 10x, I'm left with just the 2 times the 2x, right? 4x. X squared minus 4 to the 4th. This is going to cancel into that to give me 3. And so I'm going to have 10x. What's this going to be in here? On the inside bracket, I'm going to have minus x squared minus 4x minus 4. Does that actually factor?
Isn't it plus?
Why is this minus 1?
Oh, never mind.
I threw this guy in the brackets to factor easier.
How is x a common term?
Where did I? Oh, I thought this 10x was attached to that. So x is not in the first one, so this would be a squared here, right?
Yeah. Now the universe makes sense.
And so now what? We have 3x squared plus 4. Is that right? Without the x. So this means critical points of this is just x equals plus or minus.
So with x minus x equals 0, x equals positive equal.
So try minus 3, try 0, try 3. So the top this time is always positive, so we look at the bottom. Plug in minus 3 here, that's positive, right? So this means concave up.
Wait, if you're testing 0, like let's say it's a function where the answer becomes 0, do you put in plus or minus?
Where the answer becomes 0.
Yeah, like let's say like 2x squared plus x if you plug in.
That means it would have been one of the critical points that you have to avoid. You wouldn't get 0 otherwise. If you plug in 0, we get a negative concave down. If we plug in 3, we get a positive concave up. Are there any inflections? No inflections, right? Why not? Right, because these points, your function doesn't even exist there. No, INF, minus 2, 2, not in domain. So in other words, in conclusion, we know where it's concave up, we know where it's concave down. For inflection, we know there's none. It's concave up, minus infinity to minus 2, and also 2 to infinity. It's concave down between minus 2 and 2. That's everything. Now let's figure out what this guy looks like. So now let's put everything in. There are no x-intercepts, but there is a y-intercept at minus 1 over 4. Moreover, that's actually a maximum point. Do you have a question? Is there a question?
No. You just said the bottom equals 0, right?
Yes,
Yeah.
because the top is never 0. So I said the bottom equals 0.
Wait, what do you mean by the top equals 0?
3x squared plus 4 is never 0. It's always a positive number.
Alright.
So if there is only 3x squared, then we might have 0.
If it was only 3x squared, then 0 would make it 0.
But wouldn't it be like minus 4 and then divided by 3 and then divided by that?
Yeah, but you take the square root of a negative. Right? If you have 3x squared plus 4 equals 0, it would mean x squared is minus 4 over 3. And then you have to take the square root of a negative.
Okay. So that's
So it's never actually 0. Not for real numbers anyway. Okay. So what else do we have? So no x-intercept, there's only a y-intercept, so make sure you don't draw anything crossing the x-axis. Asymptotes, horizontal, what do we have? We have a horizontal asymptote at 1, right? Now, in the handout, I actually told you how to represent asymptotes. Use broken lines, right? So y equals 1 is the horizontal asymptote. You just use broken lines for y equals 1. Similarly, for minus 2 and 2, you have vertical asymptotes. Draw broken lines at minus 2 and 2. That takes care of asymptotes. Where am I increasing and decreasing? Let's put this stuff in.
Negative infinity to negative.
So I know pretty much from 0 going back, I'm increasing the whole way. And then from 0 going forward, I'm decreasing the whole way. And now about concavity. Between -2 and 2, I am concave down. And otherwise, I am concave up. And there are no inflections.
Professor,
Yes.
what's the value of that y?
This?
Yeah.
1.
How you get that weight?
It's a horizontal asymptote. I found that in the second step. Well, the third step. Okay, so what does this guy actually look like? Now, technically speaking, what you want to do is when you're approaching an asymptote, you take the right hand and left hand limits to see is it shooting up or is it shooting down. But you can actually tell that from other information. So let's actually see if we can figure it out. This is a maximum, right? Local maximum. So what should your curve be doing on either side? Everything should be getting lower. So I know as I'm approaching this one from the right, I'm actually approaching negative infinity, right? Because if I approach positive infinity, it wouldn't be a maximum, right? Similarly here. So I know the middle has to look like that, right? I'm increasing concave down. Over here, I'm decreasing concave down. I can't touch -2 and 2, so I'm stuck in between these guys, right? And that gives you the maximum. What about over here? I need to be going up. I need to be increasing. So should I be from down here increasing? Why not? Crossing a horizontal asymptote is fine. Huh? Exactly. If I actually did that, I would pass the x-axis, which I know I didn't do because there is no x-intercept, right? Which means if I'm increasing, I have to start from above the x-intercept, the x-axis, right? Now, how would I look there? So I know I'm increasing, so the asymptote is like this, right? So here's the question, how do I approach this 1? Because as I go to negative infinity, I should be going to 1. So there are a couple of options, right? I could actually cross the horizontal asymptote and then go back and settle at 1. Or I could just settle at 1 from the beginning. Which one is it? Why? Why would drawing this and just settling eventually not work? Because here I get a relative min. Because there is no relative min. So a curve like that, and that is not an option. It means I have to be like this, and I have to stay above the horizontal asymptote, right? Because if I ever go below it, I'd have to increase to go back to it, and that would cause a minimum, right? So I know that doesn't happen. In a similar way, this graph, this side has to look like that. See what I'm saying? You have to be decreasing. You can't cross the x-axis, so you have to level off before. You have to level off before passing the horizontal asymptote, because if you level off after, it will create a minimum that isn't there. Right? So that's what this graph looks like. Yes?
Took you like 1 hour to do 2 of this math. So imagine what happens with us.
What? This is a 15-minute problem. Like on a final, you should be able to do this in 15 minutes or less.
Whatever we were saying.
Huh?
Whatever we were saying.
What are we doing with this?
There were 12 questions.
Wait.
That has
Well, it'll probably take you longer than 15 minutes the first few times you do it, but that's your goal. Your goal is to be able to do one of these in 15 minutes or less.
It takes 50 minutes to write it all. It takes 50 minutes to write it all.
Exactly. You shouldn't be thinking about just going through the motions.
Finish the work and if you have like
Let's go practice. I like that.
no, I get it so many times.
No, I showed you that I had an example to it, and I'll look it
All right, let's do real examples. So now we're finally officially in 3.4. So here's your function, x squared over x squared minus 4. You're also doing that f prime of x is minus 8x over x squared minus 4 squared. You're also given that f double prime is 8, 3x squared plus 4 over x squared minus 4 cubed. And this is an actual final problem, right? So in the final, they're going to say, okay, given the function and these two derivatives, which you don't have to verify, so you don't have to check, just assume these are derivatives, right? Just assume whoever's writing the exam knows how to differentiate, right? So you're just going to take this is the rule, these are derivatives, I don't have to do that, right? So then they're going to say, make sure, find all your intercepts, asymptotes, blah, 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 and use that information to sketch the graph, right? Typically, they'll ask you for all of this in the problem, right? But they'll give you the first and second derivative. So now it's just you using, right? So let's begin. Domain.
Negative infinity to negative 2 union, negative 2 to 1 union, 1 to 2 to infinity.
Okay, intercepts. X-intercept.
X-intercept. Y has 0.
Just x equals 0. What's the y-intercept? Y equals 0. Asymptotes, horizontal.
184.
You take the limit as x goes to plus or minus infinity of x squared over x squared minus 4. In either case, you'll get 1. Vertical asymptote. This occurs when x is minus 2 or positive 2. Moving on, increasing or decreasing. I need the derivative to be 0 or undefined. This will be x equals 0, x equals 2, x equals minus 2. What? This is what it should be like in an exam. That's how you should be doing it. This is why you have all that homework. Like when you see this problem, drink your Gatorade while you're doing it. That's how it should be, right? Yes. For x-intercept, you said y equals 0. A fraction is 0 when the top is 0. This means x squared equals 0, so x equals 0. Right? For y-intercept, you plug in x equals 0, it's 0 or negative 4. That's what y equals 0.
Cross multiply, eventually 0.
No. Cross multiply, you still get whatever. Yeah.
For like an exam, we can just write the x's like that.
If you're given this, sure. Make sure you're right though. Okay, so 0, minus 2, positive 2. We're going to test minus 3, minus 1, positive 1, 3. In the first derivative, because we're doing for increasing, decreasing, maximum, minimum, right? So I plug in minus, the bottom is always positive, notice that, because it's a square. So only the top is what I care about. Whenever my x is a negative value, this will give me positive, right? So it's going to be positive here, it's going to be positive here, which means increasing, increasing. Whenever my x is positive, this will give me a negative number, so it's negative here, it's decreasing. 0 is the maximum. We're increasing from minus infinity to minus 2, union minus 2 to 0. We're decreasing from 0 to 2, union 2 to infinity. I have a maximum at 0, 0. There is no minimum. Now we move on to concavity. So I'm going to, for the first derivative, I said equal to 0 and undefined. There are only 2 solutions. So I'm going to test those in the second derivative. Now, in the secondary, the numerator is always positive, so I'm really going to look at the denominator. If I plug in a 3, it's going to be positive, which means concave up. If I plug in a 0, it will be negative, which means concave down.
Wait, you got that
By
negative
plugging
2 and 2, you just saw that in your head?
Yes. Right? X squared minus 4 equals 0 when x is plus or minus 2. Right? Am I the only one that can do that in my head? Okay, so now we have concave up, concave down, inflection points. So I'm concave up on minus infinity to minus 2, minus 2 to infinity. I am concave down minus 2 to 2. Do I have an inflection point? No, because the only possible candidates for inflections are not in the domain, so there's no inflection point. And now with that, we can sketch the graph. By the way, we've been 4 minutes at this. That's with me answering questions. Okay, so now we're going to throw everything in. X-intercepts and y-intercepts, there's only one. It hits it at the origin. Horizontal asymptote, there's one at minus 1, at positive 1. That's a broken line, 1. Horizontal, vertical asymptotes, again at minus 2. And 2. Let's do increasing from 0 all the way back. I'm increasing all the way forward. This is very similar to the last problem. I'm just showing you how much faster the process is when you don't have to slow down to take derivatives. You have to know how to use them. Just set the top and bottom equals 0 all the time because you're plugging in those x values and testing. Concave maximum, I know it happens at 0. Okay, concavity, I am concave here, concave up, in the middle, concave down, here, concave up. There is no inflection. So this is a max, so I know I have to be going down on both sides, so it's obvious how I approach these guys. And concave down, so I should shape like a frowny face the whole time. Here I should be increasing concave up. The only x-intercept is here, so I have to be above. Can I cross the horizontal asymptote? No. By the way, another way to check for sure whether you cross that asymptote or not is to actually see, will your y value ever equal 1 in that function? Right? So if you look at that function, x squared over x squared minus 4, does that ever equal to 1? Right? Obviously it never equals to 1 because the top is different from the bottom. You'd have to divide something by itself to get it. Right? So then you know it never will touch the horizontal asymptote in this case. So you could always do that as a double check. And then here we should be decreasing, concave up, so decreasing like a smiley face. I can't cross this because it never equals 1. I can't cross the x-axis because there's no, this is the only x-intercept. Questions? That was about yeah. Let's do B. Let's see if we can get through B. B is slightly different.
Yeah, the top is the x squared.
Right.
Horizontal asymptote changes.
So the horizontal asymptote is going to be different.
Yeah. It's going to be 0.
The vertical asymptotes will also be different. Okay, let's try to get through You guys want to race?
That is not even fair.
Why is that not fair?
Oh, I'm sorry, man.
Yeah, right. It's like giving us a rundown Honda versus your Ferrari.
No, I'm totally out of practice, seriously. Yeah, right. Seriously. You know the last I taught Calc 1? Forever. By the way, in all seriousness, when I was like a kid in high school, that's the kind of stuff my friends and I would do. We don't play video games, I'll race you to finish this math problem. That took a lot. Let's see who finishes first. Let's see who has a nicer solution. Mine only is 5 steps, yours is 6.
Just rather drive with it.
That happens more in programming, though. Who can finish this in less steps?
Yeah, I
Impossible.
used to do that in math. In programming, it's important though, because you're wasting processing time.
Latency, yeah. Okay. You're gonna be that one guy that just does one line. This is everyone off. It's like,
Okay, domain. All real numbers. Intercepts. What's the x-intercept?
0.
X equals 0. What's the y-intercept?
0.
Y equals 0. Horizontal asymptotes. Okay, the limit as x approaches plus or minus infinity of 4x over x squared plus 1. The answer is 0. That took way too long. Okay, vertical asymptotes. The power on the bottom is higher. Whenever that happens, it goes to 0. Okay, vertical asymptotes.
X is plus minus 1.
No,
No?
there's none. So rational function, vertical asymptotes will have when the denominator is 0. Where is x squared plus 1 equals 0? Nowhere. It's never 0. It's always 1 or bigger. So there's no vertical asymptotes in this particular graph. What are the points I have to test to check increasing or decreasing? You said the top and bottom equal to 0, right? The top is equal to 0, x equals 0. The bottom is never 0. So that's the only point you have to test. That's the only critical point. So I can plug in, say, minus 1, positive 1 in the first. Oh, we should be looking at the first. See, rookie mistake. What are the values I should be testing in this one? 1 and negative 1. I looked at the wrong thing. That's when you catch yourself in the exam. Oh, God, look at the wrong function.
I was having
Okay, your
trouble.
penalty.
I was having trouble with the domain.
Yeah?
Wouldn't it be supposed to be like negative infinity to
Oh, you
negative
can't
1?
take the radical with negative. That's not true.
No, if I plug in negative 1 for x, this is 2. That's fine.
Oh, yeah.
The bottom has to be 0 for the number not to be in domain, but x squared plus 1 is never 0. So yes? What's your question? Who said they had a question? Everyone always has questions. Yeah, okay. So where do we plug these numbers in? F prime. Notice that the denominator is always positive. Did I actually, I think I wrote down something wrong. This should be a plus. Right, the denominator is always positive, so I'm only really checking the numerator. If I plug in minus 2 into that, that's negative, which means decreasing. If I plug in 0 for x, that's positive, which means increasing. If I plug in 2 for x, that will be negative, which is decreasing. Do I have maximums or minimums? Yes, we have both of them. This is a max because it's defined everywhere, so our function is continuous and we decrease on the left, increase on the right, etc. So here we increase, decrease, max, min, We are increasing from -1 to 1. We're decreasing from -3 to -1, union from 1 to infinity. We have a max happening at 1 comma, plug into the original function to get the new ones, and I think you have what, 2? Right, 4 times 1 over 1 plus 1. The minimum would occur at -1 comma -2. Concavity, what are the critical points? Set the top and bottom equal to 0, you get 3 numbers, x equals 0, x equals plus or minus radical 3. Plug in a number, so -1, 1, 2, -2. Here we plug into the first derivative, here we're going to plug into the second derivative. Again, the denominator is always positive. What's common? Positive or negative here? It's positive? Negative. Plug in -1, positive or negative? It's positive. Plug in 1. Plug in 2. That's positive. So here, concave down, concave up, concave down, concave up. Any inflections? Yeah, let's go through them, right? Inflection occurs here, inflection occurs here, inflection occurs here. So where we concave up, concave down, inflections. So where concave up, minus radical 3 to 0, union radical 3 to infinity. Concave down, minus infinity to minus radical 3, union 0 to radical 3. Inflections will occur at 0, in which case my function is 0. It would also occur at positive radical 3, comma, I would plug in radical 3 there. The 4s would cancel, I would get radical 3. And then if I plug in minus radical 3, I get minus radical 3. Okay, now we can sketch the curve. Intercepts only the origin. Horizontal asymptote at 0. We're increasing at -1, 1.
Yeah, I'm hungry.
Now will you guys settle down? Be quiet. Concavity, we also have these guys having minus radical 3, other radical 3. So for concave up here, and here, we're concave down in the middle. And at the end, and we have inflection points at here, about here. So this is at radical 3, minus radical 3. This is an inflection. This is an inflection. This is a 0 was what? Well, nothing. 1 minus 1 was a maximum. This was a max at -1, 1. And -1 comma -2 was a minimum.
What happens to that
1 comma 1 was a maximum. 1, 2 was a maximum, which would make sense. Was that 1, 2?
How do you think what the bottom was?
So let's begin. Concave down, decreasing, I would have to look like this. Switch the concave up. Increasing concave up. Keep increasing concave up. Alright, the 0 is actually inflection, so I switch here to concave down. Switch here to concave up. This is supposed to be symmetric, by the way.
Good.
Looks like